Welcome back, ladies and gentlemen. I wanted to look at 5-5 a little bit today. I got my unit circle out, handy dandy, pretty sweet, and see if we can't make some sense of what this one's trying to do. So the big innovation here in 5-5 is a little bit of vocabulary as well as this inverse trig stuff as well. So the first thing hopefully you picked up on is that sine inverse and arc sine are the same thing. It's just different wording, means nothing crazy. The first one's on here. These ones are just, hey, can you use your unit circle backwards, essentially? Like the cosine of what angle equals the square root of 2 over 2. Well, you can grab your unit circle and say, okay, well, the cosine is the x value. That appears to happen here at 45 degrees. Kind of over here, except it's negative, so no, not down here. X is negative as well. And it happens again right here at 315 degrees, where it's positive. So 45 and 315. What you got to realize is that this statement means the angle that has a cosine of root 2 over 2. And so in an algebraic sense, I don't think I want to use that pen. Let's grab a Sharpie. In an algebraic sense, if I have the cosine of x equals the square root of 2 over 2, and I want to say solve this algebraically, well, the inverse operation of cosine is cosine inverse. So cosine inverse of the cosine of x equals root 2, right? We take the cosine, oh, well, crap. We take the cosine inverse of this 2. We'll just draw an arrow. It's fine. Wrong order, not a big deal. Cosine inverse of that. We take the cosine inverse of both sides. They cancel. And I get that x is equal to the, did I do it again? Dang it. The cosine inverse, or inverse cosine, or arc cosine, whatever, a cosine doesn't matter, of square root of 2 over 2. And you grab your calculator, you could punch this in, or you could look it up on your unit circle. If it's nice, that's fine, whatever. But the point is that this means the angle with a cosine of root 2 over 2. That's what cosine inverse of stuff means. When you see this, that's what they're asking, an angle that has the cosine of root 2 over 2. So, the rest of these, you just look it up on your unit circle. Can you do it? These ones are kind of inception-y, right? 4 is easy enough because they cancel. Root 3 over 3, done, easy. The tangent of the inverse cosine of 2/3 seems a little bit funkier. So I'm going to do a similar problem here. I'm going to do the tangent of the inverse cosine of, let's go 4/5. I'm just going to pick nice numbers so it's not quite as much of a pain here to work things out algebraically. So what this means, I want the tangent of the angle that has a cosine of 4/5. So what I'm going to do, I'm going to draw a right triangle. I'm going to put it in quadrant 1. So it means the angle is down here, my right angle. And I'm going to give that angle a cosine of 4/5. And remember that cosine is adjacent over hypotenuse. So I'm going to label it. Adjacent is down here, 4. Hypotenuse is 5. So now I have an angle. I don't know what it is. That's okay. I have an angle that has a cosine of 4/5. Its adjacent is 4 and its hypotenuse is 5. So now this asks me to take the tangent of that angle. Well, tangent is opposite over adjacent. And I have the adjacent, but I don't have the opposite. So I need to do Pythagorean theorem to get that. And 4 squared plus y squared equals 5 squared. And hopefully you're recognizing this as a Pythagorean triple, a 3, 4, 5 triangle. If not, not a big deal. We'll look that up. It's fine. There aren't very many perfect number combinations that work for Pythagorean, and 3, 4, 5 is one of them. So 16 plus y squared equals 25. If you subtract and you take a square root, you will find that y is equal to 3. Cool. Now that I know that, I now can take the tangent, the opposite over the adjacent, and thereby conclude that this statement is equal to the opposite over the adjacent, or 3/4. Looking at the problems here, I can go ahead and tell you that this one is going to involve a square root just because 2 and 3 aren't part of a Pythagorean triple. 5 and 13 are, so 6 should work out pretty nice for you. Again, this is just the cosine of the angle that has a sine of 5/13. So you draw up your triangle, make it work, rock and roll, nothing crazy. This one, solve each problem round to the nearest tenth. This is the same thing we've been doing, except now they're asking for angles, right? So in a hypothetical scenario, I have some triangle. We'll do 7, that's fine, right? I got something here. Got a triangle, and they tell me that Q is 10, and little s is 3, and they want to know that angle. Well, first thing I'm going to do is label my sides. Opposite, straight across. Hypotenuse, right there. Opposite and hypotenuse. Which ratio uses opposite and hypotenuse? So, ka, to is so, opposite, hypotenuse, sine. So I know my setup is going to be sine of my unknown angle is 3/10. And at this point, there's no trickery here. I literally just grab my calculator. I take the inverse sine of both sides, and I got that x is equal to the inverse sine of 3/10. If you're looking for your inverse sine button on your calculator, it's probably second sine or shift sine, and you do need to make sure you're in degrees for this. If you're in radians, it's going to give you a hard time. Cool. So there's that. The only new vocab here is this solve each triangle. That just means find everything. So find the angles, find the sides, things that are useful, Pythagorean theorem, and 180 degrees in a triangle. So like if B is 49 and that's 90, you can say that A is 51, and then you should be able to use sine and cosine and Pythagorean theorem to kind of fill in the blanks from there. That's that. Yeah. Rock and roll, ladies and gentlemen. Please